Welcome to the Damcasters, brought to you in association with the Pima Air and Space Museum. I'm your host, Matt Bone. Hello everybody and welcome to the show, and we're going big today, and by big I mean big airplanes and big infrared telescopes, because today we're going to be discussing SOFIA. Now, SOFIA was a joint NASA German Space Agency DLR project which put a huge infrared telescope in the back of a 747 SP. Now, the 747 SP was one of those fantastic one-trip Boeing specials. So it was a shortened 747 designed to do super long distances. And this particular one was Clipper Lindbergh, which has been renamed by NASA, which is fantastic. She flew with Pan Am and then United before NASA pulled her out of the desert, and they put a big telescope in the back of it. So in the middle of the episode, we'll have Andy Bailey telling us a bit about the aircraft, but we're going full science on this one because we're joined by Dr. Dörte Mehlert. And Dörte is fantastic. She is the head of public outreach and education for the German SOFIA Institute. So we're going to be talking about all the discoveries that SOFIA made. And we're going from water on the moon to the building blocks of everything. And it's a lot, but that's why we're talking to the head of education and public outreach, because Dörte is great. She helps us to explain some of the incredible things that are happening in the universe, or more particularly, happened in the universe, because we talk about light speed and time dilation and stuff. So, yeah, go read The Forever War. Best book on time dilation out there. So, without further ado, we're going to get into it. But as we always do with our interviews here on the Damcasters, we like to find out how somebody got into their field. So our first question is going to find out how Dörte got into all this sciencey sort of stuff. How did you get into the science game? How did your career start that led to SOFIA?
Of course, when I was in school, I was good in math and in physics, so I thought I would study physics. Mm-hmm. That's my kind of education. And then at the very end, I had to decide in which field I would like to do my diploma thesis. And actually, I found a very nice area in Hamburg where I was studying physics. And I thought that this was a nice place. So I went to the professor and told him, I haven't heard any lectures of astronomy. So no idea, but I like this field. I think it sounds interesting. And he said, oh, no, don't worry. You can get everything. You can grab it. So I started there. And then after that, I decided I would like to continue. Then I did my PhD in Munich. Mm-hmm. And then I went to Heidelberg, where I did my postdoc for about 6 to 7 or 8 years. And the funny thing was that from my diploma thesis and my PhD thesis and postdoc time, I was always changing fields. Okay. Not dramatically, but it was all extragalactic. But so because I recognized that at some point, I had the impression I went deep enough, and I would prefer to get the wider field. So now the wider view, and besides that, I really started, I started writing articles or giving talks to the public, and I noticed that I liked that, and apparently people like to hear my talks and like to read my articles. So when I was already doing my postdoc for 7 years, I think, not me, but my very best friend who does nothing with physics or math, she saw the advertisement for my job I have right now.
Oh, right, okay.
And she said, this is your job, you have to apply there. But I was on holidays with my 2 boys, and we just moved, and I had all my advertising stuff in boxes. But she said, you have to apply there, and that's what I did, and I got that job.
And so how did that job lead into the SOFIA program? Was it for the SOFIA program?
This was a job, so I'm the head of the education and public outreach for the SOFIA on the German side. Okay. So you know, SOFIA is a project between the NASA and DLR, so the US and German Space Agency. And usually NASA has an educational program for all its bigger programs. So, and then this time, or for this project, DLR did the same. So they said, okay, we will give you some money for this educational public outreach stuff. And the University of Stuttgart, where the German SOFIA Institute is located at the Institute of Space System, they gave 1.5 positions so which is a lot, just doing education public outreach. So we are the only just project that has its own education and public outreach area, which is quite unique in Germany. There are institutions like Max Planck institutions, Fraunhofer institutes that have outreach areas, but not just projects. So that's very unique in Germany.
Oh, fantastic.
Yeah, so that's why we have money to, for example, build these models, do travels and all this stuff, and we have people that are doing this work just 100%, not just besides their science, but do this education and public outreach 100%. Super. Yeah, that's perfect.
So I suppose the next big question is, what is SOFIA?
SOFIA stands for Stratospheric Observatory for Infrared Astronomy. Scientists and engineers like to have these shortenings. So if you take all the first capitals of letters of this, then you get the word SOFIA out of this. And
so did they have the name, or did they want to call it SOFIA and make the name work?
No, usually it's like they knew it's an infrared observatory, and then they try to find a name so that this shortening would give a nice word. So this time it worked very well, and it works in German as well as in English at the same time.
Super.
So that's perfect.
Now, this is, he says, getting his notes up in front of us, really, is, this collaboration, do these sorts of things happen very often between, say, because you sort of think of NASA as this big, huge thing, because of course we have ESA as well and the various partner organizations there. But do these collaborations happen quite often, or was this a unique experience?
This was also a very unique experience, because this is the only project where there's only NASA and DLR, and so only US and German side, not ESA, no Japanese or whatever space agency involved. And this came up due to the scientists that were working on the predecessor of SOFIA, which is the Kuiper Airborne Observatory, which was a US NASA project, but the scientists from the US were collaborating with German colleagues. So, and the German colleagues were on board on this, and then they thought, okay, this was I think this was a cargo machine with a 90-centimeter telescope in there. And then they decided, well, we need a bigger one. And that's how then they thought, okay, let's try to go to our two agencies and try to figure it out. It took a while until everything was set up, because in between there was German unification, and they needed the money for other things, and probably on the US side there were other things as well. So, but at the end they figured it out, and so the project started.
Because that's the thing, isn't it? This has been a very long gestating project, hasn't it? We sort of see the final product in the aircraft over the last sort of 10 years.
I mean, in the very beginning, people said, you are crazy having an aircraft. I mean, we have a door which has the size of about 4 times 4 meters, and we open it during flight. You would never do this usually. And I mean, the Kuiper had a smaller door, but anyway, they said, okay, this wouldn't work. And of course, you really had to convince people that it's going, and we had to do tests in wind tunnels and simulations and all this. But yes, it took a while.
Super.
Moreover, the project was scheduled to be, once it was in full operation mode, it was scheduled to operate for 20 years. And so anything times 20 is a lot of money. So you really had to convince people even more that it's worth doing it.
So let's get into, we can geek out about the airplane enough, but we're here to talk about the science and the things. Now, one of the things I definitely want to get my head around is what an infrared telescope is, because we've all had telescopes, we've looked through them and things, but the infrared spectrum is a fascinating element for it, and it's not what people would think a telescope is. So how does the infrared telescope work?
Well, the telescope itself works more or less like an optical telescope. It's just collecting the light. What is different are the instrument at the very end, which kind of investigate, which are kind of the eyes of the, I mean, if you have a telescope that's just collecting the light, and then your eyes will detect it. And your eyes can only detect optical light. Light is more or less an electromagnetic wave, and waves can have shorter or longer wavelengths. So you can just forget this electromagnetic if you want to. And the infrared is just, I mean, the optical is a very small part of this wavelength ranges, and the infrared just heads on at the red part of this optical, so that's why the name comes from. And it's just a longer wavelength, and and radio or X-rays is the same physical thing. It's an electromagnetic wave as well, but with either shorter or even longer wavelength.
Yeah.
And different wavelengths tell you things about different physical processes, and that's why we are doing infrared astronomy, because we want to investigate those processes where you only get the information in the infrared.
So is it because it's at that end of the spectrum that the data you'd be able to interpret can travel those sorts of distances? Because light will fade over time, so what traditionally we'd see a picture of, is it like that? Or?
No, it's just that it really tells you things about other processes.
Okay, so instead of just that sort of, it looks like this, you can see what's behind.
Yeah, I mean, every light at every wavelength travels at the same speed, depending on the medium in between, but it doesn't depend on the wavelength itself, in a sense. So the thing is that infrared information is kind of thermal information. So it tells you more or less about the temperature, kind of. And the thing is that the universe is cold. So, and if you want a huge part of the information is just in this range because of the universe is cold. So that just fits to this wavelength. One very important thing is that if we want to investigate how stars are born, are formed and evolve, those stars are usually inside a kind of what we call interstellar dust clouds, and the optical information wouldn't get out there. So if we want to learn something about this, then we need to do this in the infrared, because otherwise the information wouldn't come out of these dust stuff.
Okay.
Is this understandable?
Yes, no, that makes perfect sense. Because for me, being quite a simple soul, you see these wonderful pictures that the telescopes produce, and the German Space Agency has on theirs, NASA has on theirs. But I guess for you as a scientist, there's so much more you need to learn just from what the visual would give you.
I mean, for example, a nice example is that the processor of SOFIA, as I said, the Kuiper Airborne Observatory, it discovered the Uranus, the planet Uranus, also has rings, but you don't see this in the optical. You can only see this in the infrared.
Really? I always thought they always knew that just from...
No, this is...
Okay.
Yeah, so for example, this is something very, I mean, you can describe this. And the same is, if you look into the sky, I mean, there is, we can't, even if we could see through our atmosphere, we wouldn't be able to look inside this infrared or in this star-forming regions, because the infrared light or the visible light wouldn't come out, but only our eyes only detect the visible light. So if we want to understand these processes, we have to do this in the infrared.
Now, where it starts getting interesting, and this is where you start putting telescopes on airplanes, is our atmosphere does a wonderful job of filtering radiation and parts of the spectrum out. So when you get, so that's why we have observatories on mountains and things, and of course telescopes in space. What does having a telescope at 30 or 40,000 feet allow it to do?
Well, the good thing there is, or the bad news is that our atmosphere, even if we have a blue sky like today, there is water vapor above us. And this water vapor pretends the infrared information to come down here, because it would be reflected, absorbed, whatever. So if we had eyes that would only detect far infrared light, then we wouldn't knew that there are stars above, even in the night, if there's water vapor. I mean, even at clear skies, there's water vapor above us. So, but if you are at an altitude of about 12 to 14 kilometers, which this is the altitude SOFIA was kind of operating and flying, then we have more or less 100%, 99% of the water vapor below us. So we have a free view in the infrared sky. And that's the reason, so if you want to do infrared astronomy, you have to get above this water vapor. You can do this with satellites. If you go, for example, on Mauna Kea or whatever, then you are only at an altitude of 5,000 or 4,000 meters, and that's not enough. You have to get higher. Satellites are also an opportunity. There's advantages and disadvantages to both. The advantage for an aircraft is that it comes down every morning in this way. So you can do maintenance on the telescope itself or on the instruments.
Yep.
You can develop new instruments and put them at the observatory. This is something you cannot do at a satellite because usually if you have a telescope on a satellite, you say, okay, this is the way how we are going to do it, and then it takes you, if you are very fast, 10 years, but usually 20 years or even longer until it will be launched. And so all technology which is launched into space is old.
Yep.
It's reliable, but it's old. In SOFIA, we could use the very first front of technology stuff on the aircraft. So that's important. For example, for one of our instruments, the people were able to make the sensors more efficient from one year to the other, about 30%. So we only needed 30% less observation time.
Okay.
So you don't earn any money from this, but it makes the observatory more efficient.
Yeah. So it's that ability to learn about how the sensors are working, improve on the sensors, and then immediately deploy them and
this
continue
is one
that
advantage.
sort of thing.
The other advantage is that at satellites you are kind of limited in space and weight. In SOFIA, of course, you're also kind of limited in weight, but not that much. And for SOFIA, we all in all, I think we had, if you count all of the instruments, 8 or 9 instruments available. On a satellite, usually you have 3, if you're lucky, 4 or 5 instruments available. So the number of kind of scientific questions you can ask is limited much more.
Okay.
This is another advantage. And of course the maintenance stuff. You can just maintenance the observatory, the instruments, everything, yeah.
Super. So let's talk about the instruments on them, because you brought a great diagram of the different ones, because it's not just one big telescope on the back, it's a number of different ones. So let's see, we've got Fifi LS, we've got Great, we've got Forecast and Hot, great names. What are we looking at when we start talking about all these different instruments?
Okay, one important thing is that on SOFIA, our instruments was mainly focusing on doing spectroscopy.
What is spectroscopy?
Yeah. So the
word I can barely say.
One thing is you can just take an image, like we see if you take a photo, that's an image. Spectroscopy is like, that the sunlight has different colors, that's a different wavelength. And so if we really want to investigate the different wavelengths, then we have to split up this spectrum of light.
Okay.
So that's what spectroscopy does. So, and the thing is that, for example, different chemical elements, molecules, whatever, they have kind of fingerprints at particular wavelengths. So we can investigate the chemistry in the universe by those particular lines at particular wavelength.
And so that's what these different sensors are going to be doing.
Yeah, this kind of graph shows you, this is kind of the wavelength range we had, and this is kind of the resolution in wavelength. So how sharply can you discriminate between one wavelength, color, to the other? So this can be, for example, if you just have a very broad filter, then you have just an image.
Yeah. If
you make it very sharply and just want to know whether it's 1 micron or 0.56 microns more or less, then you need spectroscopy.
So for a layman, it's how you're zooming into that big image.
Not in the image, but in the colors.
Oh, right, okay.
Because the colors tells you something about the chemistry, about the elements or the molecules in there.
Okay.
So
let's talk about some of these different ones, because let's start with the German ones. Okay. So which were the German ones?
You want me to tell you what the shortenings are meaning? I try to. Okay, maybe I should have looked that up. So
they're your toys. I hope you know what they are.
But we only call them with the shortening names. But I will figure out. We have mainly there were 4 big instruments, and there were 2 German and 2 U.S. instruments.
Okay.
I hope that none of the other instrument PIs would blame me on that statement. The first light instrument, or one of the first instruments that was mounted was GREAT, which is a German receiver at terahertz. That's what it means.
There we go, yeah.
You know, I have to look at the shortening, then I get it. And this is a very particular spectrograph, because it's kind of a radio, and it's, as you can see in the graph, the resolution in spectrum, the spectral resolution is high. It can discriminate wavelengths at about 6 or 7 digit after the comma.
Oh wow!
So it's
right past the decimal point.
Yeah.
Right,
so that's it's kind of a radio. You kind of tune it on a very particular wavelength, and you just listen, kind of. Is there something or is there nothing? So if there's something, then you have a line.
Okay.
So otherwise, there's no signal.
Okay.
So it's not good in kind of getting a broad spectrum, but only this very tiny things. But this is sometimes very important. So that's what GREAT is. So that's what you can also see here. So it has these very short wavelength ranges in there. And then we had this is also going to the very far infrared. So we have the infrared is kind of also discriminated into 3 parts: the near, mid, and the far infrared, which just means the shorter, mid, and the longest wavelengths. So, and GREAT was one of the instruments that was sensitive to the very longest wavelengths, so something between 30 and 300 microns, if this tells you anything. And the other German instrument was FIFILS, which is called Far Infrared Field Imaging Line Spectroscopy, spectrometer. Spectrometer or spectrograph.
Correct, that's what I've got on my notes.
Okay, perfect, so I'm not that bad. And FIFILS is special in another thing, because FIFILS can make an image and a spectrum at the same time, so it saves you time. Of course, you have to pay for this in a sense, because that means that the image resolution is not that high, then compared with an image or with a camera which just makes image, and the spectra are not that well resoluted don't have that such a high resolution than, for example, the GREAT spectra. But you get the same, or the spectral information and the spatial information at the same time. So that saves you observing time.
So would you use the sort of the high-ish resolution camera to then decide where you were going to point the other
Usually you would start with a lower resolution and see whether there's something. And if there's something, then you go to a higher resolution, either in space or in spectrum.
Because you're looking at the black bits of space that we would see from down here.
Right.
So it's not looking at the stars we can see, it's looking much further beyond.
It might be the same stars or the same things, but other information from the stars. So
the stuff that's in the black bits is the interesting stuff.
Yeah.
Okay, so then we've got the NASA ones as well, which are further over on the side.
The very first instrument that was mounted on SOFIA was where we did really astronomy with, was the forecast instrument. This is now, this means, what does that mean? I would have to look it up.
Yeah, that's fine. Forecast is good. Is a good enough name for it. What did it do?
Forecast is mainly an imager.
Okay.
It was kind of the imager of SOFIA,
which
also could do spectroscopy, but with a low spectral resolution, as you see here. So you could split the colors a bit, but not that good then.
So this was the higher resolution one compared to FIFILS, which was the lower. Were they sort of comparable between the two?
The thing is that forecast was doing really an image. And the difference is that forecast is working in the mid-infrared. So between 5 and 28 or whatever, something 30 microns. So at the mid-infrared and FIFILS and GREAT were observing at the far infrared.
So it's all of the different instruments that are on there are working in harmony at different parts of the wavelength.
Yes.
So it's not one for everything. It's each one doing each bit.
That's again, as I said in the beginning, that every wavelength tells you things about different physical processes, and so astronomers are interested in very different
Yeah.
arrays in the physical area. So forecast of course tells you much different things than GRADE can tell you.
Okay. And HAWK.
HAWK Plus is also a very interesting GRADE instrument because HAWK Plus can indirectly measure magnetic fields in the universe. The area of magnetic fields is not new, but it's in a sense you have to measure it indirectly because magnetic fields kind of
Do you see the result of a magnetic field as
you
opposed?
see the result, but indirectly, and because it's indirect, you need really good signal, good light. So that's why these magnetic information is not that easy to get, especially in the longer wavelengths. So in HAWK Plus is an instrument that can also do images, but one, I would say, the really greatest scientific results HAWK made were in the magnetic field area.
Okay.
So
we've got a fantastic sensor suite on board the aircraft looking across the spectrum.
Right. And this is, for example, the advantage over satellites where you just have only maybe 3 or 2 instruments, and here we have much more.
Super.
So
let's get into what you found.
Okay.
Because there was a lot.
Yeah.
And we'll have to pick a few of our favorites here. Because there's, oh goodness. I suppose the easiest one to start with is water on the moon.
Yeah, this is true. This was done by forecast, and the thing was that, people already know that, we know for a while that there is water ice at the poles on the moon. But for example, if you whenever want to have a village on the moon, you have to have resources up there. And water is one of the most important resources because it has hydrogen and oxygen inside. So, and that's both what human beings need.
Yes.
So, people knew that, or there were hints that there were kind of some OH things up there, but OH is not water.
Yeah.
That's H2 plus an O.
Yeah.
plus an oxygen. And there is one line which is only kind of emitted by water, where you can really say if you find this line, then it has to come from water. It's not OH. It's around something like 8 microns something.
So this is the reflected light from ice, or what would it be? Or the molecules?
This is kind of, it's...
I told you I was going to ask you some simplistic questions.
Well, it's not really, I mean, the stuff up there wouldn't kind of, it's a good question. This is the molecules in there, they kind of emit the light. As I said, and light is different wavelengths. And so, but light does not usually only have kind of, emits continuously, but some molecules, if the molecules might be H, water is 2H, 2 hydrogen molecules and 1
H2O. Yeah.
Imagine you have this kind of molecule, water, having these H2H's and 1 O, and there are these balls, and there are springs in between, so they vibrate. And these vibrations make the frequency when they have a particular frequency where they would work on. And this is kind of correlated to the light frequency, so the wavelengths we would detect.
Okay, so you're looking for that vibration.
Right.
Okay,
so this is kind of the molecule kind of vibration in there. I can't tell you whether this is whether it's this kind of vibration or this kind of vibration, but it's a vibration in there. And so this kind of, the people said, okay, if we would detect this particular information at this particular wavelength, then we would know it would come from water and not from these OH stuff. So, and that's what they did, and they found this in areas on the moon, honestly to say more in kind of shadows areas, but they found hints that there was much more water not only on the poles, but on the surface on the moon that they thought would be before. And that is very important for these missions to the moon if you want to be there. So if we have much more, it's not a huge amount of water, but it's more water than we thought, and every milligram we have up there is good because we don't have to bring it up there.
Yeah, because you can make fuel out of it,
Right.
and you can breathe it,
Yeah.
and you can drink it.
Yeah, yeah.
So it's
yeah.
those three
Yeah.
fantastic things.
Yeah.
That was huge,
Yeah.
and especially as someone who spends, we're spending a lot of time watching For All Mankind.
Yeah.
So you're like, oh, I can understand that. Now let's get into some of the more tricky things.
Yeah.
Because water people can get. So what is helium hydride?
Okay, our view on how the universe, or at least our universe we know, started was with the Big Bang.
Yep.
And in the very beginning, the only molecules that had been before stars were formed were helium and hydrogen. So that's an H and helium. So
Yep.
they had been there at the very first, not very first side, but they were the first atoms that evolved. And so the thought was, okay, then there were kind of, the theory of the Big Bang kind of tells us that at some point, the first molecule that should have formed should be helium hydride. Why hydride? Hydride is a hydride atom without an electron. It's a proton.
Oh, right, okay.
So a proton is just hydride in this sense. And so this kind of theory says, okay, then at some point, the first molecule that should have formed should have been helium hydride. But we cannot look that far back in time when this happened, and the signal probably also would have been very little. So, but then people had another idea that there are, planetary nebula are situations when a star is dying, then it kind of explodes, and part of his material is ejected out into space, and so you have this what was kind of ring around this leftover of the star. So this is called the planetary nebula, and there is a front, which kind of the shock front, where this material kind of hits the other stuff in the universe or in the surrounding, and then the astronomers thought, okay, at this kind of shock fronts, we should have the same temperature, the same materials, mainly helium and hydrogen, and the same pressure.
Okay.
So if we have the same physical conditions, the same input, then we should also see helium hydride be formed.
Okay, so you're theorizing around what would have happened at the beginning, but at the end, you can then say we should see those same things happening at the death of the star as you would at the birth of the star.
So what we detected with SOFIA was not a helium hydride molecule from the very first side, but we detected that it had really formed in space in the same conditions than we think had been at the very beginning of the Big Bang, or after the Big Bang in the universe.
It's still present, so we know that it's been there for the whole time.
It is still present, and we can detect it. And this is kind of, astronomy is a bit different because you usually cannot go wherever and really prove that you are right. You always have a theory, then you have measurements, and if the measurements still match the theory, then your theory can still be correct. It's not a guarantee that it is. So that's the thing. So in this time, then we detected the helium hydride, we can say, okay, our theory about the Big Bang is still valid. It still can be true.
Still can be true, okay.
In a sense, yeah.
See, the thing is, if I tried that during one of my exams at school, it wouldn't work, which is why astronomy is fantastic. It's kind of there, yeah. We're going to take a quick break to pop to the Pima Air and Space Museum to visit with Director of Collections Andrew Bailey and find out about one of the aircraft in the incredible Pima collection.
Hi, I'm Andrew Bailey, Director of Collections here at the Pima Air and Space Museum. I'm here today to talk about our newest acquisition, a unique aircraft that we're really excited about adding to the collection. And you can see it right here behind us. And that's the Boeing 747 SP SOFIA. It's unique in two different ways. First, a Boeing 747 SP. I'm sure a lot of you have heard of what a Boeing 747 is, but many of you may not know what an SP is. During the 70s, Boeing came up with an idea of that they needed a different aircraft, a smaller aircraft that was a wide body that could compete with other smaller wide bodies like the DC-10 and the L-1011. They also wanted an aircraft that could fly long distances without having to refuel. So they came up with the 747 SP, which is essentially a 747 with a shorter fuselage, about 47 feet shorter than the 747-100, a taller tail, and other different changes. They allowed the aircraft to fly at higher altitudes and longer distance. The first one was delivered to Pan Am in 1976. It flew Pan Am's longest route, which was from New York City to Tehran in Iran, nonstop. A year later, this aircraft went into service with Pan Am and was named Clipper Lindbergh, named after the famed aviator. The aircraft also spent time flying with United before retiring from airline service. Only 45 SPs were ever built, partially because they were just too expensive to maintain and to fly, and also newer airliners were coming out that could fly farther distances with a cheaper cost. So what does SOFIA stand for? SOFIA stands for Stratospheric Observatory for Infrared Astronomy. That means this aircraft has a 19-ton telescope mounted inside it. SOFIA was a combined project with NASA and the German Space Agency. Many space objects emit their energy in the infrared wavelength, which means they can't be seen through a traditional telescope, which is why this aircraft has an infrared telescope. SOFIA flew her missions at 45,000 feet, flying 99% above the infrared blocking atmosphere. This allowed the telescope to see things that ground-based telescopes couldn't see. SOFIA was also mobile. This allowed her to fly literally almost anywhere in the world to take observations. Northern hemisphere, southern hemisphere, even out over the ocean where there are no ground-based telescopes. Despite all this, last year, NASA and the German Space Agency decided to retire SOFIA. We are lucky to have SOFIA retire here to the Pima Air and Space Museum, where she will be displayed along with other NASA aircraft like the Super Guppy, the Vomit Comet, and the NB-52A X-15 mothership.
To find out what's going on at the Pima Air and Space Museum and to see the incredible collection that they have, please visit www.pimaair.org for more information, and be sure to give them a follow via all the links in the description to this episode. And now, back to the show.
Okay, so that's interesting. So through SOFIA, we're able to start drawing a line back to moments after the Big Bang. But then at the same time, you've got observations of stars like I'm going to mess this one up, the Betelgeuse, which is in and of itself special. How? Because I remember that making the news.
The thing is that this is a kind of a red giant, which is kind of one kind of star, and our sun is in a sense a little boring sun or star, which is just a sun in which it stays in the same shape for a few million years.
Nice and stable, which
billion
we like.
years. Yeah. So this is. Now I'm in the US. So in the US it would be billion. So.
As opposed to hundreds of thousands of millions. Yeah.
10 times to the ninth years. So, and it stays the same. In the very end, it will also explode. But there's other more massive stars that kind of explode much earlier, and then they start kind of extending, but they will not blow out of their material right then they would shrink again, then they would extend again. So at some point they would really explode. And the question was in this hand, and when they, for example, can explode, so I think Betelgeuse probably, I think in Germany we say Betelgeuse. Don't ask me how people pronounce that in
No,
English, I don't know.
I struggle to pronounce anything in English, so it's fine.
People would think that it would end in a supernova, and the big question was, is this now already the start of the supernova explosion or not? So, but it turned out that it was shrinking again. So,
All right.
it was extending, so was getting brighter within a few days or weeks. I think this event was only for 2 weeks or something. I don't have it in mind. So, and maybe 4 weeks. Don't name me on this, but for astronomically kind of time scales, this is short time scale.
Very, very fast.
Yeah. And so, but then it didn't, and it shrinked again. So, but everybody was very excited whether we could kind of really view an explosion right now, more or less in front of our garden. So, yeah.
So when it started shrinking again, everybody got a bit disappointed.
If you want to say it this way, yeah.
Because I suppose the thing that is fascinating is what we're really talking about is a time machine, isn't it? So we're seeing things that have happened hundreds of thousands of years ago. So even something we're looking at it over 40 weeks. It's been gone. It probably has exploded for that because we're not seeing what's happening outside our window.
Yeah, this is due to the fact that light is traveling at a limited speed. So that's so that if signals coming here from things that are at different distances, then it tells you immediately things about different epochs. So that's just it. Yeah.
I find that fascinating.
Yeah, it is. It is.
Looking up at the night sky and thinking some of that stuff's not there anymore.
Yeah.
And it's mad. So there was the Galactic Nursery as well. Is that right? I get Galactic Nursery. The galaxy. That's not a question that was on my list. But what else were some of the observations that you made? Because there's, like I said when we were chatting, the list was very long, and I was just picking some of the bits and pieces.
I mean, as I said, one of the very main goals Sophia was looking at was star formation.
Yeah.
Maybe I should tell you. Maybe you know. I already mentioned that helium and hydrogen were the molecule or the atoms that evolved before stars, and all other chemical elements in the universe evolved in stars due to nuclear fusion. And stars usually form out of a huge cloud of dust and gas, whatever, and if it's heavy enough that it would collide under its own weight, then it would do, and then about a few hundreds up to 1,000 stars would form at once.
Okay.
So
it's not a star forming, it's many stars forming within.
And the interesting thing is that there are a lot of small stars which would evolve much slower, and the most massive ones would evolve very fast, and they would kind of burn helium and hydrogen to higher elements like oxygen, all these other higher elements, and then they would explode they would explode before the smaller ones are doing their evolution anyway.
So they burn out very quickly.
They burn out, they would explode, and their material would be implemented in the forming of the smaller stars.
Okay.
Which happened with our sun and with our planetary system. And so that means that all chemically elements that are in your body have formed, which is not helium and hydrogen, have been formed in the stars. So we are all stardust.
So it wasn't just David Bowie who was a starman.
No. And now the thing is that, as I said, the star formation always happens when it's dense enough. So, and the densest area in our galaxy is the center of our galaxy, where there is a black hole, which is just a huge mass, or very heavy thing. It's not huge, it's comparatively small to its mass. And so it's really making a dense environment. So this means that this is the star-forming region in our galaxy. That's why we were looking into this galactic center to investigate how stars would evolve there, form and evolve there.
Direction in space is a terrible thing because there isn't really one, is there? So when how do you? Is there certain periods through the year that you would be able to take those observations for it? Because our positioning would be in different places at different times. So, or can we see the center of our galaxy at all times? Because I suppose that's one question, is because we're always moving in different galactic places.
The thing is, the center of the galaxy, you can mainly, or the best you can observe it from is from the southern hemisphere. Okay. That's because our planetary system, or the plane of our planetary system is kind of bended by about I think 23 degrees to the plane of the of our galaxy. Yeah. So that means, you can draw this, that if you're on the northern hemisphere, you have to be close at the equator so that you would be able to see
down into you're sort of like that.
Yeah. So that's why if you want to investigate the galactic center, you should best do it from the southern hemisphere. That's why once a year we went down to New Zealand with SOFIA.
Okay.
Because there is a National Science Foundation. They have this Antarctic Center down there. And so when there is their winter, it's our summer, our nights are short, so better go to the southern hemisphere. The nights are longer.
Long nights.
And it's winter there, so they wouldn't be able to go to the Antarctica. So that's why we could go there and use their facilities.
Super.
And that's where we went, for example, to investigate our galactic center. Also some other, a lot of other objects, but the galactic center was one of this.
So what was that sort of big takeaway from the galactic center, seeing these stars forming?
One thing was that we could kind of, with the forecast instrument, we could kind of, you cannot see the galactic center, or the black hole in there, but you can see its how it works on its environment.
Okay.
So, and we could kind of trace the way where the material would fall into this black hole. This was interesting. That's something we could do with the forecast instrument. And another thing which we did with the Hawk instrument was, we know that not only our galaxy, but all galaxies probably have at least one, maybe even 2 or 3 black holes in the centers. And some black holes can be very aggressive, and they kind of push out jets, and they are really, you wouldn't really want to be in there or close there, or sometimes the energy or the light coming out from this centers is so bright that it will kind of shine, that you wouldn't see the galaxy itself because the center is so bright. And so they are very, very active galactic holes or centers of galaxies. Okay. And then there are galactic centers which are kind of quiet like ours. And the question was, why is this? Why can they be so different, although the galaxies may look very similar? And one reason might be the magnetic fields in there, which we measured with Hawk. And it just, so the magnetic fields can either kind of increase the energy which is coming up there, or they can smoothen it out. That's what we took out of this.
This goes back to being able to measure the effect of those gravitational
of the black hole and all the how explosive or how intense the processes in there would be. Yeah.
I suppose to the layman we just think a black hole sucking everything in and that's that. But there's more going on around it.
Yeah, of course. I mean, it's sucking in, but then it's getting denser, and so the energy has to go somewhere, and then some energy is going to be pushed out. That's what we sometimes see in jets of material and light. But that's what we sometimes see if the centers are very active, and our galaxy doesn't have a jet. So why is this? So that's good, probably, or that's probably good for us.
Yes, we like a nice stable sun and a benign center to the galaxy. So for you, I suppose instead of me asking you about various different things, what was the highlight of the, I suppose from an educational purposes as well, from your main job, what is the discovery that SOFIA made that is most exciting to you? What's your favorite one? Is I'm trying to ask.
Actually, my personal favorite one is really this galactic center stuff. I really find this very interesting. And the other thing is even more if you kind of take this information and then try to adopt this to other galaxies. Because I mean, all stars we see in the night skies are all belonging to our own galaxy. So there's only 3 objects in the sky which you may be able to see with your skies, which are extragalactic, which is the Andromeda galaxy, which is in the northern hemisphere, and which is the small and the large magellanic clouds, which are in the southern hemisphere. And everything else is the stars here. And so, but we are able to kind of extrapolate the information we have from our galactic center, and then we can observe other galaxies, and we can kind of interpolate in between this information. That's something I really find is very fascinating. So
you're starting to be able to chart how those differences work, and then the effects that they have on other galaxies.
Right. Yeah.
So let's, SOFIA was supposed to last for 20 years. It unfortunately hasn't, and it's now parked just over there behind us. Is it just because it was a terribly expensive way to do science? Was that the reason it came out? Does it just come down to money in the end?
Maybe or no, definitely I'm the wrong person to answer that question. But my opinion is, I think it is, the argument, the official argument was that it would be too expensive, at least on the US side. This is hard to say, what I would say, because as I said, SOFIA is operating very different, like from I mean, what do you want to compare SOFIA with? There is nothing.
Yes.
The only thing is satellites.
Yeah.
But they are very different, because once they are launched, then the operational money is not that much. SOFIA starts every night, so of course it's very different. It's like comparing pears with apples. So, and the thing was that this observatory was kind of started in a sense that it should get better and better and better, which is what a satellite cannot do. It's getting worse and worse and worse because the systems fell out.
So we're coming back to that incremental improvements every time it goes.
Right. So it's and yes, of course, and in this sense, it was true that in the beginning, SOFIA was not sufficient, not that efficient than a satellite was at the beginning, but this was not the approach. At the end, I mean, on the German side, actually, we were very efficient from the very beginning on, because
the Germans being efficient, I'm shocked.
Yeah, this is and definitely mainly due to this great instrument, which was built by the Cologne colleagues from the University of Cologne and the Max Planck Institute in Bonn. And as I said, GREAT and FOCUS were the two instruments that were mounted first, and GREAT was the first German one, and they produced a number of papers. I would think the highest amount of papers that SOFIA produced were coming from the GREAT instrument. I hope that nobody from the US side would blame me on this, but I think this is true. And so on the German side, we were very efficient. So usually politicians would kind of say, okay, how many scientific papers do you get out of $1 or euro? Yeah. And in this sense, SOFIA on the German side, with the German instrument, we were very efficient. On the US side, in the beginning, it was not, which does not mean that the colleagues were doing bad jobs. It was just that the instruments were just working differently and just took more time to get everything set up and getting better. Yeah. So, but at the very end, shortly before we were kind of shut down, we were, if you would compare us with the Herschel satellite, which was infrared satellite as well, which if you want to compare it with a satellite, then you should compare it with Herschel. Yep. Then we were all in all at the same efficiency level than Herschel was. So in this sense, this argument from my side doesn't make any sense. I think it was just a political decision because as I said, any amount of money times 10 or 20 is a lot. So, and you can only spend $1 and euros once. So you have to decide what you want to do with this. So at some point, the people just decided that they want to do other things with this. Personally, I think it's very unusual because it was April 22 when NASA and the DLR said that they would stop this program. Usually, if you would do it, you would say, okay, we want to stop it. We were doing it right in a process of call of proposal, which is when scientists could kind of apply for observing time. And they announced the stopping right in that time. And usually you say, okay, make this call, finish finish the programs that are ongoing. That would take you another 2 years or whatever, and then we ramp down everything. But what they did this time was announcing it in April, and in September we had the last flight. This is absolutely unusual, and this is really a sad thing because there are some projects or programs which couldn't be finished. So, this was not a very clever decision from my personal point of view. The other thing was, I think, mainly a political decision.
So the aircraft is here at the Pima Air and Space Museum, like we were saying. The telescope isn't here. It's back in Germany.
No, that's not true. The telescope itself is here, but what we took off was the mirror.
Aha,
the main
right,
mirror,
okay.
The main mirror of the telescope. And this is still in Palm Day, where SOFIA was allocated, or where we were doing the observations from. And but the mirror is going to be shipped to the German Optical Museum, which is allocated in Jena,
Okay.
which is being built upright or rebuilt, and which will open in 26, I think.
Okay.
And they will want to build their new building around our mirror, so that's why we ship it there. Yeah.
Fantastic. So, what is your favorite memory of the program?
As you said, when I was applying for this job, and I learned that we had this education and public outreach program, and the idea behind that was to take visitors on flight on SOFIA. So we had media persons on SOFIA, so it's a shame that you only contacted us right now,
I was thinking that I
few years
started all
ago.
this too late. Yeah.
And we had educators flying on board of SOFIA. And the idea behind that was to kind of get the educators so excited that they go back to their classes and get all the pupils excited to go into natural science and engineering science. So that was the kind of idea behind that. And it was always so fascinating seeing this kind of sparkling in the eyes of the people flying there, and just having the possibility, of course, I mean, we know that California is exciting even without SOFIA, but of course going here, this was, for example, DLR was paying the money for the travel.
Yeah.
So, and the University of Stuttgart paid us for kind of advising them there and being with them. And so they came here, they had the challenge to come to a NASA base and speak with NASA people. I mean, NASA is kind of bureaucratic, it's an administration, but it's just fascinating.
Yeah.
So, and this was always so great, just having the possibility to make other people so happy just with bringing them there and giving them the opportunity to be on board and chat with all the people on board and get into this. This was really, that's really a great thing.
That's wonderful.
So, and although SOFIA is stopped much earlier than it was supposed to be, I'm so grateful that I was able to work on this great project. So.
Wonderful. Well, thank you so much for spending some time with us to take you through it, because we're going to be out doing some filming on it later, and hopefully with you tomorrow. Yes, because they can't put steps on it because of the Super Bowl.
Wow.
Yeah, the people watching the Super Bowl have today off, so that's the reason.
I can tell you another story. You may. I don't know which year this was. I went to Mountain View, where the science center of SOFIA was, and close by there is Santa Clara, and I don't know which year it was, but I was making my booking and I was wondering, why the heck is the hotel so expensive this weekend? Usually I was coming in on Saturday so that I just get a little bit adapted to the jet lag.
Yep.
So I came in on Saturday, and the night from Saturday to Sunday and Monday, it was so expensive. I thought, why? And then a colleague of mine told me, okay, yeah, there's Super Bowl right in Santa Clarita, which is 20 kilometers from where I was staying. So, and all the NASA people were told, please take a day off on Friday and Monday. But this time, I mean, it's in Las Vegas.
Yeah. Well, it was here in Phoenix it was up in Phoenix last year.
Yeah.
So it's all been around there, but terrible.
Yeah.
But there we go. There we go. We'll get to see you later. Thank you so much for spending some time with us. It's very, very kind of you.
I cannot thank Dörte Mehlert enough for joining us here on the Damcasters, and that was a lot to take in. So I can highly recommend checking out the links in the description below to all of the information packs that are available online to go through. There's fantastic animations and sort of little PowerPoint presentations that break down some of the science that NASA and the SOFIA Institute have been putting together. Now, if you want to see the aircraft, she is on display now at our fabulous partners at the Pima Air and Space Museum. On Tuesdays, you can go through her and have a look. And it is really, really something. It's great to be able to have a look at a 747 SP, as there's only about 3 left in the world, I think. But to climb around her is fantastic. So that's included in your price of admission. So get there on a Tuesday. Otherwise, we'll put up some videos, sort of the longer version of our little wander around in it we'll put that up at some point as well. So, as always, thank you for your support of the show. Like, subscribe, leave a comment, put some stars in your podcast apps of choice if you could. Tell your friends. That all helps the AI overlords to bump the show up the ratings, because we've got lots of really fun stuff coming. Loads of the things that we filmed out at Pima, I'm still working through the edit on. It's taking a while. I apologize, but we'll be getting that out over the next few weeks. We're going to be talking Kennedy assassination. We're going to be talking about Operations Manna and Chowhound, which were the aid drops to the Dutch people at the end of the Second World War. Now, you would have seen a bit of Chowhound at the end of Masters of the Air. We're going to be looking at that from two angles, so watch this space on that. But thank you for your support. If you want to join us on Patreon, we've got the group chat thing going on there. Lots of discussions. We've got our next social coming up in May, right after I watch Fulham get beat by Manchester City. So, yeah, that'll be fun. But until then, thank you so much for your continued support. Thanks for watching the show. And until next time, do take care of yourselves. Bye-bye. The Damcasters is hosted and produced by Matt Bow and is a Boney Abroad podcast production. To learn more about our podcast and check out our previous episodes, head to www.thedamcasterspod.com.